Hello and welcome back to Python. And now I want to show you a library which is called Numpy or Numerical Python, which is a larger library, so I'm gonna split this tutorial into separate parts. And yes, this library is kind of the base library of other libraries regarding data science. And it is working with large multi-dimensional arrays and matrices, along with a collection of mathematical functions which you can operate with. And because of NumPy relies to C code, the structures work pretty fast and are efficient regarding storage. So instead of further explanation, let's dive into it. So the installation is pretty simple. You just have to install NumPy with the pip installer, or yes, like me, like the lazy one, just using import NumPy, moving your cursor around and click on install NumPy in the IDE called PyCharm. Maybe it's possible in other IDEs in a similar way, but other IDEs have a console as well, so you can just type in pip install. As a quick reminder, the basics of Python are kind of requirements to use NumPy libraries. So in this tutorial I won't explain anything regarding the basics. And with the basics I mean the very basic like loops, conditions and common data types and lists, because arrays are kind of related to lists. And let's start. After importing NumPy, let's for example create our first array. So to create an array in NumPy, we will first create a list, like list1 equals 1, 2, 3, 4, 5. And now we create our first array, which is NumPy point array of list1. So now let's print both. Print our list1 and print our array. And as you see, the output on the console is quite different. But apart from that, how you are working with the data types is pretty similar. You can get access to the first element of the array with array and index 0. And if you type in length of array 1, it should return the length of our array. So why should you use arrays instead of lists if they work pretty similar? And that's just based on the simple fact that NumPy uses C code, and lists and arrays nearly look the same but are not the same. So for example, lists are existing of nodes. You can, for example, look at a list like this. We have list element 1, which points at list element 2, which points at list element 3. And as a user of Python, you don't really see that, but if you, for example, want to access to a certain element of a list, let me type the rest. So last element is list element x. So for example, if we want to get access to list element 3, he has to kind of search every list element and has to compare it if it is list element 3. So you don't use indexes, or the interpreter you don't really use these indexes. So you can, of course, when you're coding, you can just say print list2 and he will give you the second element, but in real time the code is not that efficient, because he's not looking at list index 2, but he's searching or kinda looping through the list. And arrays don't do that. An array you really have, because it's using C code, he's getting access at the element of the list. Kind of that. And because in NumPy we are using arrays instead of lists. Maybe you know arrays from C or Java. Arrays have the pro or have the advantage that most operations are much faster, and for example, when you have really large arrays with 1 million elements, array operations are so much faster, so much more efficient than list operations. And for this, but this only counts for larger arrays. They don't use that much storage than a list. If you have really small lists compared to small arrays, even it is even that the list is a little bit smaller regarding the storage than the array. But if you have larger arrays, and in data science you always have large lists, large arrays, the array uses much less, no, not much less storage, but for example 20% less storage. So the advantage in case of storage is real. Okay, but what can we do with those kind of arrays? So we have our array 1, and yes, if we, for example, want to multiply each element of our list by 2. For example, we have list 1, and what we want to get is 1, not 2, 4, 6, 8, 10. We have to multiply every element of the list with 2. For example, print E for E in list 1, and E multiplied with 2. And now I messed things up, which is because, yes, it is list 1, 2. And now we increased every element of our list with 2. Simple thing, you probably know it. But for our array it's much simpler, because you maybe know it in math. If you see it as a vector, you just have to type array 1 multiplied with 2, and every element of our array is multiplied with 2. Same goes for plus 2. Now we add 2 to every element of our array, and also we can add an array to an array. And now every element of the array gets an element of the other array added, and that's for example, the first element gets added with the first element of the other list, and so on. So we get this result. And the same goes if we subtract the arrays. This should be 0 at any element. Yes, it is. And we should be able to multiply them. Yes, now every element is multiplied with the same element of the other array. And at last what I wanted to show is that we can determine what data type the elements of our array have. What do I mean with that? The function I used was numpy point array of list 1, and we can give this function another argument, and that can be numpy point integer 16. So why do we use that? Because we are saving much more storage, because now every integer in this array only uses 16 bits, which is 2 bytes, and the maximum number you can now use should be 2 to the power of 15 minus 1. Why not to the power of 16? Because 1 bit is always the bit which defines if a number is negative or not. Complementary, I guess, was the right name. And of course, because the number 0 takes up 1 space, you can only use the remaining bits for a number. So now, after using my calculator, I got 23,767. So this number. And of course you can use integer with 23 bits, integer with 64 bits, and yeah, don't let yourself be fooled. In PyCharm, 128 bits are possible to choose, but if you now click 1, he will give you a attribute error because NumPy has no attribute integer with 128 bits. Okay, this is everything I wanted to tell you. I hope you kind of enjoyed the video and see you on the next part. Have a good evening, day, dinner time, whatever time it is. I had to stop the video at many times because I got ill. Yeah, and yeah, I don't wanted to record my coughing, but I hope that's okay. See you, bye bye. Hello and welcome back to Python with another part of the NumPy series. Yeah, and today we are focusing on the dtype attribute, the dtype attribute, which means we have to dive a little bit deeper into data types in NumPy by general, because yeah, we need to understand data types for working effectively with Python, with NumPy, because the dtype function or declaring your own variables in general is one of the reasons why NumPy data types work much more efficiently than regular Python data types. Okay, in our last video we created our own array, and yeah, we looked at the data type we could specify while creating an array, and yeah, we realized int 128 was not possible, but int 64 should work. Yeah, it does. And the argument we are giving to the array is the dtype. So if we type dtype, we already hit the right argument. It is dtype stands for data type. Obviously. No big surprise, I guess. And we can also print dtype, of course, np dtype of, yeah, array. Oh, it's yo. Okay, perfect. So, by the way, what I forgot to mention, I changed NumPy in NumPy as np because always saying NumPy point data dtype is a little bit too long, so we are just typing np. It is commonly done, so I'm doing it as well. Okay, but enough of that. Let's kind of uncomment, or no, let's put our last lines of code into comments, and let's just print the dtype of our array. And as we see, we can't construct a dtype out of an array, but we can use it as an attribute like array point dtype. Yeah, and now we get integer 64 because we said the dtype of the array is integer 64 with 64 bits. Same goes for 32. Or this should work as well. E4. Yes, it does. So what is E4? E4 is also read as an integer with 23 bits, because as you maybe know, 1 byte contains 8 bits, and E5 means integer with 4 bytes. So 32 bits means 8 bytes. No, means 4 bytes. Oh, I'm kinda messing it up today. Yeah, let's try it again. E4 means 4 bytes, and 4 bytes mean 32 bits. Now I got it. Sorry for the mistakes. Okay, and obviously if we now print our dtype, it gives us integer 32. Let me see. Yeah, if we're using E2, we are having 2 bytes. 2 multiplied with 8 is 16, so we got our integer 16. The same goes for E8, I8, and that's kind of cool. We can even use or declare an unsigned integer. So that means it can even use one bit more, because unsigned means just absolute or positive integers. So because there's no number smaller than 0, we can use the 1 bit which defines if the number is positive or negative, and use it to create even bigger numbers. And so we got more storage in our bytes for the numbers. And what's even possible, what's kind of cool, we can use complex numbers. Default by 128, but we could also use 64, which doesn't work because I forgot NP. Now it works, NP complex 64. Or if we wanna use the string variant, we can also use strings like we did before, C and a 8, and we got 64, obviously, because 8 multiplied with 8 is 64. So like already mentioned in the previous video, because you can kind of choose by your own which data type is used, you can save storage, be more efficient, because you can decide how many bits are used, how many bytes are used. And yeah, if some operations only use small numbers, you can decrease the number of bits or bytes which are used, and yeah, you save storage and the code gets faster. And yeah, at last what I wanted to show is defining your own D-type, where we can use our constructor, which is implemented on D-type equals np point D-type. Okay, now let's create our own D-type. So we have an array, or a list, how you wanna ever call it. The D-type constructor looks like this. Let me first create something, and then I explain how and why I created it. So we have weight and yes, E2 and name as 20. And now we can create an array. Let's just name it array2, which is np array. And yes, we have someone who weighs 84 kilograms, and his name is Joss, and a girl who weighs 69 kilogram, and her name is also Josh. And now we can use our very own D-type, like D-type equals own D-type. As you see, there's no exception. And now if we print r2.dtype, of course we have to print it. We get the D-type which is printed, which is weight E2 and name S20. And as you can see here, here is a less than sign, like an operator. And what that means, we are looking at our next video. And for that, I wish you a wonderful evening, night, dinner time, whatever time it is. I hope you could understand what I was trying to explain. See you in the next video. Bye bye. See you. Hello and welcome back to Python, back to Numpy, with our third video now about byte arrays and the difference between big and little endian. This is, by the way, a video can kind of skip, so you can skip to the fourth part because most of the time it doesn't matter which byte order is used if you don't alter the default byte order. So if you don't set the byte order, you won't have any problems in general. But if you're more into binary data serialization or file formats and using binary file formats, knowing something about byte order or even how to specify the byte order in Numpy arrays can be useful. So watching this video won't make you dumber or more stupid, I guess. Okay, but what is a byte order? Byte order is the order in which individual bytes of multiple byte data types, integers, floats, stuff like that are stored in your memory. And yeah, it depends on the byte order how a computer represents and interprets the bytes. For example, there are two common byte orders, the little endian and the big endian. And if we are using an AMD or an Intel processor, it will most likely be the little endian byte order. This simply means that the least significant byte is stored at the lowest memory address and the most significant byte is stored at the highest memory address. And yeah, big endian, it's the exact opposite, so the most significant byte is stored at the lowest memory address and the rest you can think it's obvious. So in Numpy you have the byte order attribute and you can check the byte order of your Numpy array, or you can even specify the byte order. But usually it uses the byte order of your system by default. And let's just have a look how you can get the byte order. So we have our array, which are the numbers 1, 2, 3, or 23, 4, 56. And if we type in r.dtype point byte order and we want to print it, it will give us an equal sign, which means the native byte order of your system is used, which is in most cases the little endian. Okay, now we want to create our or specify the byte order. As already told, you can dtype, you can specify your dtype, for example, an integer with 4 bytes. And if we are using the sign, we will define the byte order. Now we are using the native byte order. Let's print the array, by the way. And yeah, we are getting our equal sign because we said it is equal I4. And this will get also the equal sign because our system uses little endian. And now we are using the big endian because, yeah, greater than means that the big order endian should be used. So to get rid of any confusion, of course, the array will always be the same. The byte order just defines how the bytes are stored, not how the certain array is presented. So the content will always be the same no matter how the byte order is. Yeah, this was a kind of short guide or tutorial. It was just some minor topic I didn't want to skip. And yes, I wish you a wonderful evening, night, day, dinner time, whatever time it is. See you in the next video and bye bye. Hello and welcome back to Python and back again to Numpy. Now we are looking at shapes and how to reshape certain arrays. So first of all, what are shapes? Shapes refers to the dimensions of an array. For example, let's create an array with one dimension, which is... Okay, first let's import Numpy. Import Numpy as np. Let's create an array. With one dimension. Let's create an array with two dimensions. And last of all, let's create an array with three dimensions. So if we print the shape of our array, like print np point shape of array 1 and click on 1, I executed the wrong program. So if we print our first list, we get 4, and yes, only a 4 followed by a comma. And the tuple means 4 is the length of the dimension, or the size of the dimension, which is 4. And because the tuple has only one element, it means we have one dimension. Now let's do the same for our second and third array. Now we did the same for the second and the third array. And to the second array, which has two dimensions, the tuple has two elements. Yeah, the first dimension has a range of 3. The second dimension is range of 2, because yeah, there are two lists inside or two arrays inside the array. And yeah, the third array has 3 dimensions, because there are 3 arrays in the array. And yes, in the arrays there are also 2 arrays, and so on. We can even get it higher to even 4 or 5 dimensions, but I guess how it's going, because I guess you understand how it's going and how it will end. What is important is it will give us an exception if we have an uneven number of elements, or if the elements of the first array and the elements of the second array in a two-dimensional array, for example, don't match. Or in our third array we have arrays which contain other arrays, and if we would add another array which only contains one array instead of 2 arrays, we would also get an exception. It's a value error setting an array element with a sequence. The requested array was an inhomogeneous, that's the shape after one dimension. So this is inhomogeneous. I guess I pronounce it wrong, but yeah, you guess obviously what I'm trying to explain. We have to add another element to this array, and now it works again. But because I increased the size on both arrays, we have now a size of 4. Now let's reshape our first array. So next to the shape we have the ability to reshape our array to another array which has, yeah, or can contain other dimensions. For example, we can move our one array one second, and the argument the reshape functions take is, and by the way I should use my array, and the argument the reshape function takes is, yeah, a shape. So we can use 2 and what happens now, it prints another array, but now a two-dimensional array, and it splitted the array into two separate parts. So we have a two-dimensional array. Each element has each array in the array has a size of 2. So we first had one dimension and the size of 4. Now we have two dimensions with a size of 2. And we also can reshape it into a three-dimensional array like this, but the second dimension only has a size of 1, so it doesn't really make sense to increase the dimension. Again, what is important, the arguments have to fit with the size and the dimension of the array. So this won't work because, yeah, we have we can't switch into a one-dimensional array with 2 elements, or vice versa. We can't have 2 dimensions with only 1 element, because, yeah, the number of elements in this array must fit to the number of elements in the new array. So the integers in the tuples multiplied have to, yeah, be the same, or have to be equal to the, yeah, length of the array. So array with 8 elements, we can make, for example, 4 2 or 2 4 as inputs, or we can even use 2 2 2. Now let's create an element with 8 elements, and now we can reshape it to 3 dimensions like this. And yeah, again, because if we multiply 2 with 2 with 2, we get 8, and 8 is the length of the array. So you can keep in mind, must equal length of array 1. Now let's try one thing. Let's reshape our second array. And when you try it, you get a value error because, yeah, 2 2 has the size of 4 and our array has a size of 16. So this will work because, yeah, he kind of unfold our array to an one-dimensional array, and now we'll repackage it. So you can, yeah, it's hard to imagine. I try to imagine as with packaging and repackaging. So we have, see it as packages. We have one packages with 4 elements. We have 4 of them, but by reshaping, he puts every element out of each package and puts them together in 2 packages, which contain 2 packages, which contain 2 packages, which contain 2 other packages. I think with that in mind, you may be able to, yeah, kind of understand what I'm trying to explain. And that's everything regarding the shape and reshapes functions in Numpy. I hope you could understand what I'm trying to tell you, because the shape, in comparison to our last video, the shape function is really important for future videos and future stuff. So but it's kind of easy to get when you beginning to understand it. So have a nice evening, day, dinner time, whatever time it is. See you in the next video. Bye bye. Hi ho, and welcome back to Python, and welcome back to Numpy. Now we are heading to our next topic, which is slicing. You may know slicing from lists, and as a quick reminder, we are just creating a list which contains 5 elements. And what we are gonna do, we want to print a list, but the list should be A, but only with 3, 2, 3, 4. So we are printing A, but we are slicing it. We are excluding index 0, so 1, which we are typing, is included, and we are excluding index 4, because it starts from 0 and ends with 4, and the last index we are typing in will be excluded. So we got 2, 3, 4, and we can take double steps, and then we are having 2 and 4 because 3 is kinda left out. And if we want to reserve a list, we are typing this little code, because now we are hitting from we are starting from the last element, which is 5, and that there is no number means that it can do it like open end. And if we only want 5, 4, 3, we are saying we are starting with 5, including it and excluding index 1. Now we got 5, 4, 3. So that's everything about slicing lists. And now we are creating a Numpy array. A equals np point array of list. And what works with lists works also with Numpy array, but it gets interesting if we have 2-dimensional arrays. So what I did now, I created a 2-dimensional array, and it has the 2-dimensional array contains 2 1-dimensional arrays, and you wonder what will happen if we print A now. Nothing. So let's explain how to get access to certain elements of our list. So we are printing list and getting the entire 2 array element. If we are typing to double point, we are creating the second element, because we are saying he should start from index 1, going to open end. So if there would be more arrays after the 6, 7, 8, 9, 10, he would include them. And now we have type a comma, because we got our line. Now we are in, you can, if we have 2-dimensional arrays, you can see it as a matrix. And after lines, we go to the columns. And here we want to start at index 1, excluding index 4. And now we got nothing, because I am slicing a list, but I wanted to slice the array. Now we got it. 7, 8, 9, because 1 means he starts from index 1 to open end, and 1 to 4 means he starts at index 1 at the 1-dimensional array, and also adding index 2 and index 3, and 4 is excluded. Now the same with a 3-dimensional array. Here I copied a 3-dimensional array, and as you may know, if we just type print a and the same we did before, he will start from the second 2-dimensional array, including the third 2-dimensional array, because we have 3-dimensional array containing 3 2-dimensional arrays. And yeah, in the 2-dimensional arrays, he will both start from the second line, because the first is excluded, and go to 4, but because there are only 2, he won't print any line fewer than the second one. Okay, to gain the same as before, or let us print out 27, 28, 29. So because there's no array after, we can say start with 2, then we are saying start with 1, then we are saying start with 1 and with 4. And as you see, we have 27, 28, 29, exactly what we wanted. And the same if we want it reversed, we are starting with 4, ending with 1, and -1. Now we got the same thing reversed, but we included index 4 and excluded index 1. We want to exclude 26, and yes. Now we got it reversed, 29, 28, 27. Last but not least, let's look at a 4-dimensional array. Now I got a 4-dimensional array, this one. I created really quickly just by adding random numbers in each element. So now let's see what happens again. Now he's giving us again two-dimensional arrays, but we want to only 277. Oh no, let's just have 127, 173, and 174. So how do we gain access? Because we are having 4 3-dimensional arrays, and we want, I guess, this one. I was referring to this 2, this 3. But no, that's too easy. Let's try to print out 317, 318, 319. So let me mark it, because I'm kind of short-minded and will forget it after seconds. We want to print out these 3 numbers. So first let us say starting with the second and excluding, or starting with index 2 and excluding index 3, then starting with index 1 excluding index 2, and then starting again with index 1, and starting from index 1 to excluding 4. And here we go, 317, 318, and 319. And it won't feel any different if we add 5, 6, 7, 8, 9, 10 dimensions. So that's probably everything about slicing. You can try it yourself, you can find new combinations, or can have an array. I will link this array in the description below. You can try new combinations of slicing and try to find your very own pairs of numbers. See you in the next video. Bye bye. I hope you could understand slicing, and bye bye. Hello, welcome back to Python and welcome back to Numpy. I hope you are in the right mood of coding and you are as excited as me, because today we are gonna handle 3 new functions, or no, 2 new functions and 1 old function. But what we are gonna do, we have this array we already had in our last video, but now we simply want to make a one-dimensional array out of this array. And how to do that, I will show you today. So I guess I accidentally deleted one square bracket. No, I didn't, it's printable. So let's first create a Numpy array out of our old array. And as you see, there are many dimensions. It's a 4-dimensional array. We want a 1-dimensional array, so we are just typing OO equals AA point reshape, not revel. But yeah, it's written like that. And now if we print pp, we are getting a 1-dimensional array. So you can imagine it is sorted like, every square bracket was deleted except the first and the last one, because otherwise it wouldn't be an array. But every other square bracket is deleted now. And we can even define an order. At the moment we are just using the native order, which should be C. Yes, it is. And as you can see, he's just starting with the first element of the first 1-dimensional array, goes to the second 1-dimensional array, so on. What we can also do, we can type an FSN keyword for an order. And yes, now you see the order is quite different, because after the 1, which is the first element of the first 1-dimensional array, he jumps to the second 3-dimensional array, looks at the first 1-dimensional array and prints the first number. Then he goes in the next 3-dimensional array, printing the first number, and so on. Then 122 is in the fourth 3-dimensional array, the first number. And after that, you could think he goes to the 6th, but no. He will get to the next 2-dimensional array and is printing the 11. Then he will also get to the next 2-dimensional array of the next 3-dimensional array. And getting the 411. So if you had a 2-dimensional matrix, he will, using F as an order, he will usually use the columns instead of the rows. But because we have a 4-dimensional array, it is kind of more complicated. So just keep in mind, first element, first element, first element, first element of the 3-dimensional arrays, and before he uses the second element, he will jump. Then again he dives in, but now he skips the first 2-dimensional array, heading to the next 2-dimensional array, does it with every same of the 3-dimensional arrays, then the third 2-dimensional array, and then after, it should be 271, we'll finally head to the second 1-dimensional array of the first 2-dimensional array. So 6 is after he got everything out of the 2-dimensional array, at least one number of each 2-dimensional array. Then he finally reaches into the 1-dimensional array. It's like being as much diverse as possible. You can maybe, use that as a quick reminder. So that to the orders, we have a similar function which is called flatten. Does the same, except it makes a new copy of our array, making it a little bit less efficient. But on the pro side you get a copy. And if we don't want an exact order, we can just use reshape. Reshape we had in our last video, What we are gonna do, we want a one-dimensional array, so the tuple has only one element, and -1 means he should fill it so that the tuple is able to be a shape tuple. So for example, if you have 2, he will set up this one-dimensional arrays so that the shape is possible, the reshape. And yeah, of course, -1 will be always possible because you can stuff everything into a one-dimensional array. And that does everything the previous functions did, but with the C order you can't have the F order in this one. Okay, this is everything for today's topic. I hope you liked the video. See you on the next video. Bye bye. Have a nice evening, day, dinner time, whatever time it is, and bye bye. Hello and welcome back to Python, and welcome back to Numpy, and welcome back to, okay, I forgot what else. So yeah, now we wanna look at 2 other functions in Numpy, which are row stack, column stack, and yes, I'm a big liar because there is a third function which is called concatenate. And I already created 2 NumPy arrays, so we can just start with today's topic. And yeah, first let's use the function row stack. So let's use row stack. So np.row. So with row stack, using these 2 arrays as an input, we are creating a second array, and the second array is a two-dimensional array containing the arrays above as rows. So if we print result, I guess we use some additional brackets. Yes. Now it's finished. We have our two-dimensional arrays containing our rows. And yeah, we can also use column stack. And now he does nearly the same, but he is, yeah, using the first column as a first row, and yeah, the second column as the second row. And that's everything about column stack and row stack. But there's another function which nearly does the same, and this is concatenate. Yeah, the function I had trouble pronouncing. But yeah, the next function I wanna show you is the concatenate function. And we are typing np.concatenate. We are typing np.concatenate. Okay, it is concatenate. Okay. Yeah, that's the issues I have as a non-native speaker. Please forgive me. So if we're typing R1 and R2 and axis equals 0, using brackets again and a comma, we are creating a one-dimensional array because he's using one axis and trying to put everything in a row. But we can also use axis 1, but then we need a two-dimensional array. Yes, and what he did now, he kind of fused them together, so he got a two-dimensional array, yes, and that is containing the first row of the first array and the first row of the second array, combining it to one row. And again, maybe it will be more clearly if I do this. So I'm defining another array. And yes, I'm putting them together. So now we are getting our array, and he's combining the first row of the first array with the first row with the second array. We can try 0, and he will use the first row and then the second row, then the seventh row, then the third row without fusing anything. And axis 2 shouldn't work because we are only in dimension 2. But it could work if we add another dimension. So let's do that. Okay, we did it, I guess. And now let's change the numbers a little bit. And now he's able to do the axis 2 thing, which is combining the first row of with the first row of the second two-dimensional arrays, then doing the same with the second one, and the second one will be put into the next one, and so on. And again, axis 3 shouldn't work. We have to move to the fourth dimension, but this is maybe topic for another video, or more like an experimental video. Here I just wanted to show you these functions and want to say see you on the next video. Have a nice evening, dinner time, whatever time it is. Bye bye. Hello, welcome back to Python, welcome back to Numpy with another tutorial, and this time we are gonna break the outside world, or the wall between this world and the outside world, because we are saving arrays in txt files, and we are also loading arrays from txt files. And to do that, we are using two functions. The first one is called saveTxt, and the second one is called loadTxt. And we already have this cool four-dimensional array, but as an input of our function, which is called np.saveTxt, we need a two-dimensional array. So we should reshape our array np.reshape, and input was AA and a tuple. Let's say 4 minus 1. This should work. No. Oh, okay, we have to save this as AA first, so let's save it. AA equals np.array from A. Guess it's called A. And to save this txt file, first we have to name our txt file, which is called coolest txt ever existed.txt. Now let's run it. And yes, we reshaped our 4-dimensional array into a 2-dimensional array and created our first txt file. And yeah, because this doesn't look that good, we also format it using, we can, with %i, we are formatting it to an integer because we got floating point numbers. Now we get integer, and in this new formatted array. And yeah, what's important is first step, first argument, the name of the file, second argument, the array, and third argument, you should consider to format it as if you don't have floating point numbers. But if you have floating point numbers, you should kind of shorten them, because otherwise they will be 12 to 13 characters long, and you don't want your input so long, to be that long, because we want to make them readable for other for maybe other programs or other functions. We can use an we can use a delimiter. Let's just use a colon. And now each number is separated with a colon, can be useful for CSV data. And yes, we don't have to use E, we can also use X, was I guess for hexadecimal. And now you have hex digits, which is kind of cool. And the same goes for %string and so on. Now let's load our file. np load. No, wait, before we are loading it, let's try a 2-dimensional array as an input. And as you see, value arrow accepted 1-dimensional array or 2-dimensional array. So if we are just making a 1-dimensional array, he is able to do it, as you see here. But yes, 2-dimensional arrays are not, 3-dimensional arrays or higher are not possible. Now, but finally, let's load the txt again. First the name of the file. And what's also important, we have to reuse our delimiter, otherwise he can't know how to interpret the colon. That will confuse him. So let's just print it. And now we got the problem. He tried to interpret float 64. So we have to say format X. Okay, I'm sorry, I was wrong. Format isn't possible. It has to be dtype. And let's use integer 64. He doesn't know how to interpret the A. Okay, he seems to have trouble with converting hexadecimals back to integers. Maybe if you have a solution for this, write it down in the comments, please, because I don't have one. So what we have simply to do is using a string, or we can use a string, or we can say format %e, And yeah, then he can load the file and convert it back. And that's how you load and save txt files in Numpy. Everything I know so far. Maybe you have something to add, please write it down in the comments. See you on the next video. I hope you could learn something. Sorry for the confusion. Bye bye. Hello and welcome back to Python and welcome back to Numpy. And yeah, what makes me a little bit sad is that this is the last video of the Numpy series. Maybe I will make another Numpy video if I realize I forgot something which is important. But yeah, as planned, this is the last video. And yeah, kinda hard to say goodbye, but yeah, so it is. Today we are gonna look at the random package of the package Numpy. So for example, you have numpy.random, and yes, random, as a quick reminder, with random you can create your own random integer with the old random package, not the Numpy random package. Like this. You can define a range, and then you will get random numbers between 1 and 4. Or you can just define a random float. And you can also define random choices of a list or of a sequence. And yeah, that was just a quick reminder. Now in Numpy, the random functions are much more complex, or can be much more complex. For example, let's first start with random.rand. So random.rand does, random.random? Yes, random.random does the same as the random.random of random, because I imported random.random as from the Numpy package does the same as from the random package. But, and here it gets interesting, we can define a shape. For example, if we use just a 4 as an argument, he will give us a one-dimensional array with 4 floating point numbers. And yeah, just keep in mind that the random only has one argument. For example, if we have 4, he will give us an error because he thinks I gave him 2 arguments, so giving him only 1. So we have to use extra brackets to tell him we are using a shape now. And now we got a 4.4 matrix, or just call it two-dimensional arrays for rows, 4 columns, and so on. We can do it 3-dimensional, 4-dimensional, and so on. And it's a simple and quick way to define arrays with certain numbers. If you want just an array for testing, you can just do random. And if you want random integers, you have, like in the random package, you have the randint. And because the arguments are slightly different, he now thinks we want a randint between, or a random integer between 0 and 4. I guess. Yes, excluding 0, I guess, but he gives us random numbers because he's interpreting the numbers differently. So this should give us, yes, I forgot a bracket. This should give us an integer between 0 and 4. This should define the shape. guess we have to define the argument. I guess it was size. No. Oh, because I'm in the print function, that's why. So yeah, there we go. We got a two-dimensional array, but let's do it a little bit more interesting. Now this is a 4.4 two-dimensional array, 4 rows, 4 columns. Yes. And like before, we can even increase the number of dimensions. If we want to get things more messy, we can also use rand integers for the sizes. Now we are creating arrays with different sizes, and yes. Outcome can be quite interesting. Now let's add some deviation to an array. So let's print rnd point normal. Now we have a matrix where we can choose. Yeah, we can choose the standard deviation, for example 0 or 2, which means we can have numbers from standard deviation of 2, and yeah, the size should be 10. And yes, of course it can be lower than 0, but yeah, the standard deviation is 2. It should be even higher than 4, should be possible. Yes, it is. By the way, they are floating point numbers. The normal function doesn't have dtype as an argument, but yeah, there are different ways to make integers out of it. And like in the random package, also Numpy random has seeds. Big difference, in the Numpy package he wants integers. And yeah, now it gets interesting because we have to set the seed again if we want to use the same deviation. Also we are using a random function here and here. Of course, because we are using the random package, the size of our arrays will always be different. So if we are using Numpy random package, it should be the same size depending on the seed. Yeah, it is. Okay, and yeah, we have to set the seed again if the second array always have to be always the same depending on the seed. So here now it stays the same. Okay, that's interesting. Maybe it was the random package, but again, what I wanted to say is that you can set seeds like in the random package. But now I'm curious. So yeah, here he always creates the same array. Now let's switch back to random. Delete random seed. Yeah, now he switches. Maybe yeah, that's really interesting. If we don't use the random package, the seed of the Numpy random package also goes for the random normal, and yeah, I've learned something as well. Perfect. And strange. Maybe if you know what the issue is, you can write it down in the comments, but I wouldn't call it an issue. I would call it something nice I discovered. So for the next subject or topic, let's first create a list which contains 3 elements, and let's create possibility containing 3 floating numbers. Oh no, let's be more specific. What's just important is that the total number of the elements has to be 1. And now for our last act, let's create an array containing only these 3 strings with these these are the possibilities, the percentage possibilities. Let me create an array, then you will probably know what I mean. So again, you have, like in the random package, you have this choice. Then you can say a one-dimensional array, which is listy. And then we create the size, which again is our tuple, the shape. And last but not least, let's do the possibilities. Look how it is called. It's just a p. P equals possibility. And let's print it. And here we go. Most of it's monk. We got an array containing monk. And do we have at least one ape? I saw one. Yeah, there's one ape. Let's do it again. Oh, here's one ape, but no monkey. Do we get a monkey? Come on. Here's another ape. Man, that's why I suck at casino games. Monkey, monkey, monk, monk, monk. Where's the monkey? I want a monkey. Here's an ape. Come on, monkey, monkey, monkey. Maybe you saw one and here's another ape. I won't finish this video until I saw a monkey. Ah, there's a monkey. Here we go. And that's it for Numpy and for random. I hope you had fun while watching my video and me searching for the word monkey. And see you on my new videos. It will take some time until I make a new Numpy video, but I hope you liked my series. I will make a supercut in a few days, and it will be about 1 or 2 hours. But for that, have a nice evening, dinner time, whatever time it is. See you on the next video. Bye bye, goodbye, and adieu.